Hello everyone. In this lesson, we're going to go over the formal limit definition for sequences. So we're going to consider what this statement, the limit as n goes to infinity of a sub n equaling L, precisely means. So here's our formal limit definition for that statement. Now you've already seen limit definitions like this before in Calculus 1, so this is going to mimic the limit definition for functions, but it's going to be just a little bit different. So a sequence is said to have a limit L, written like this, right? So that just means that the ANs are getting closer and closer and closer to this number L as n gets larger and larger and larger. If for every number epsilon greater than 0 that you are given, you can find, or there exists, another number capital N, and that's usually going to depend on the epsilon, so it's going to be a function of the epsilon, in which the absolute value of AN minus L is less than epsilon, which is the same as saying this, that the ANs are always going to be between L minus epsilon and L plus epsilon whenever little n is bigger than the capital N that you found. So that's the formal limit definition. Now let's look at this graphic down here to try to get a little better understanding of what's going on. And let's consider this example while we're doing it. So let's look at this graphic. So we would like to argue that this is true using that epsilon n limit definition. Now right here we have the sequence graphed. Right here these dots are these sequence values. Now remember, these dots, the way you plot them is you actually plot n comma n over n plus 1. So that point right there is 1 comma 1 over 2. This point is 2 comma 2 over 3, and so on. Now you can see from this graphic that it does look like these dots, the y coordinate of these dots, are getting closer and closer to the value 1. This is the line y equals 1. Okay. Now we need to argue that for every epsilon greater than 0 that you're given, you can find a capital N, a number n, now usually that's going to be a function of epsilon, in which this is true. Such that this is true whenever n is bigger than the capital N that you found right here. Okay, so for n bigger than capital N, or whenever little n is larger than capital N. So let's graphically argue why we can do this with this graphic. So in this graphic, the epsilon as we have it drawn here is actually 0.3. So this distance is 0.3 and that distance is 0.3. So this point right here is 1 plus 0.3, and right down here is 1 minus 0.3. So in this case the epsilon is 0.3. That's what you're given. Now keep in mind that this statement right here is the same as saying n over n plus 1 must be less than your limiting value 1 plus epsilon, or greater than 1 minus epsilon. Now this is the same as saying that your dots must remain between these two bands, right? They must stay between these two values here. That's what this is saying right here. Well, we can see that if we let the epsilon be 0.3 in this case, that as long as we take little n bigger than, let's see, this is 1. This is when little n is 1, 2, 3. Now you see, once we get to 3, we are inside that band, and the dots stay inside the band as long as little n is bigger than 2. So with the epsilon being 0.3, which is what we have right here, we would choose capital N to be 2. Okay, now suppose we make this epsilon right here a little smaller. We must be able to find this n no matter how small we make this epsilon. Okay, well, suppose we make the epsilon 0.2. Let's see what would happen. Well, graphically, if we change that to a 0.2 over here, all right, let's see what we need to pick the capital N to be. Well, now you see, to stay inside this band, we have to pick little n to be bigger than, let's see, 1, 2, 3. Now that might be on the band, let's say, so 5 or larger. Okay, so in that case, if epsilon is 0.2, we should pick the n to be 4. Okay, 1, 2, 3, 4. So we see that as long as little n is bigger than 4, like 5, 6, 7, the dots will be inside that band. Let's do it one more time. Suppose we pick the epsilon to be 0.1. Okay, what should the n be? Well, let's change the graphic here. Okay, well, now it looks like we need to pick that capital N. Let's see, for these dots to be inside the band, this is 1, 2, 3, 4, 5, 6, 7, 8, 9 might be on the band. Looks like 10 or larger. So we should pick the capital N to be 9. So then if little n is bigger than 9, so 10 or larger, you see this is 10, 11, 12, and we will remain inside that band. Okay, maybe one more time. If we make the epsilon, say, half of this, let's say 0.05, let's see what the capital N should be chosen to be. Okay, so it looks like in that case, let's see, it looks like that dot right there is going to be inside the band. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like the capital N should be like 23 in that case. Okay, but you see, the point is, no matter how small I make this epsilon, I can find this capital N so that these dots will be inside this band. In other words, this will be satisfied down here. This is going to be satisfied as long as little n is larger than the capital N that I find. Okay, so it looks like no matter how small I make that epsilon, I will be able to find that capital N. So it looks like this statement right here, that the limit as n goes to infinity, n over n plus 1 equaling 1, does satisfy that epsilon n limit definition. Now let's take a look at how would we actually prove this analytically without just looking at it graphically. How would we prove this statement analytically? So let's look at this example now. Now here we want to actually prove analytically, in other words, without just looking at the graph, we want to prove mathematically that this statement satisfies that epsilon n limit definition. So in other words, we need to prove this, that if we're given some small number epsilon greater than 0, we need to prove that we can find that number n in which the sequence a sub n minus the limiting value in absolute value is less than epsilon whenever little n is larger than the capital N that we prove we can find. Okay, so what we do is we start out with this. We actually start with this statement right here, and we try to deduce, in order for this to be true, how large does little n need to be. And so we'll just manipulate this statement mathematically to try to figure out what that capital N needs to be. Okay, so we start out with that statement right there, n over n plus 1 minus 1 less than epsilon. Remember, that's the same as saying an minus our proposed limiting value is less than epsilon. Okay, so we start out with this, and we're going to manipulate it. So notice that we can simplify n over n plus 1 minus 1 like this. That's the same as 1 over n plus 1, right? That's just by cross multiplying, right? Or finding a common denominator. Rewrite the 1 as n plus 1 over n plus 1. Okay. So you see you get n minus n plus 1 over n plus 1. So that's going to be, okay, so actually I should have a negative right there, okay, but I'm taking the absolute value anyway, so it's just going to become a positive 1 in the next step. So in the next step now, so you see we have this. Now in the next step, we just get rid of the absolute values and we rewrite it like this. So you see we have 1 over n plus 1. Now keep in mind this is always positive because the n is supposed to be bigger than or equal to 1, right? We're taking the limit as n goes to infinity, so we can assume the little n is going to be a large number, large enough so that this is always positive. Okay, so this statement right here is equivalent to 1 over n plus 1 less than epsilon. Now we can manipulate this. Okay, so let's just fill in a little detail right here. So if we multiply the n plus 1 to the other side, divide the epsilon over, we get, and then subtract the 1 over to the other side, we get that statement, which is what we have right here. Okay, now these are if and only ifs going all the way down here. What that means is if this statement is true, then this is true, and we can mathematically go backwards as well. So we've determined that if this statement is true, then this statement is true. So in other words, this is going to be our capital N right here. This right here. So as long as little n is bigger than this capital N right here, then this statement will be true. We can go backwards, right? There's nothing wrong with going backwards here. And then we can go backwards here. We can just take the absolute value here and put a negative in there. And then from here we can go back to here. So we've deduced that as long as little n is bigger than 1 over epsilon minus 1, then this will be true. And so we've proven that we can always find this capital N right here. And that's it. That completes our proof. So as you see down here, that's what our capital N should be chosen to be. Okay, so for example here, if you are given a really small epsilon like 0.01, then what should you choose this capital N to be? Well, the capital N in that case, so the N of 0.01, would be chosen to be 1 over 0.01 minus 1, which would be, let's see, this is going to be 100 minus 1, so you would choose capital N to be 99. And there you go. And so that concludes this example.